Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another installment of Math 212, Calculus 2, the new and improved version, where we are covering series. And we looked at what series were. We looked at series convergence tests last time, and now we are going to continue. So that's not actually what we're doing. Let's actually recap before we jump into it. Okay, so one, we did, let's actually stop the video as well. So one, it is new and improved. I mean, I wasn't kidding. Like Calc 2 a year ago was completely different from what it is now. And we didn't do series in that, and we didn't do any 3D stuff in it. So now we have Calc 2, we do series in Calc 2, and we do some 3D stuff in Calc 2. So yeah, it's new and improved. All right, let's do a quick recap just to see what were the important ideas from last time. One important idea is how to approach series convergence problems. So if I have a bunch of series, if I give you a series and I ask you to determine whether or not it converges, determine whether or not it converges absolutely or conditionally or whatever, that's a little bit different. I'll get to that. Essentially, there was a general approach to approaching series and knowing whether or not they converge. Test for divergence, always high up on the priorities list there. You should be able to eyeball most things that diverge. If the limit does not go to 0, that should be something that you can quickly see right away. So we always try to apply the test for divergence right away. It's almost like applying a basic rule or integration by substitution for a random integral. It's one of the first things you think about. And when it does work, it works very quickly. So it's not always going to work. It's not always going to give you a conclusion, but when it does, it's going to be one of the quickest things you can do. Another one depends on how a question is phrased. So if a question asks specifically what a series converges to, for you guys, it basically means you know it's geometric because there's no other series that you can tell what the answer is. The geometric series converges to a over 1 minus r specifically. So you can actually compute that. In general, telescoping series would be another problem type that shows up here, but you don't have to worry about that. Or if something asks about absolute convergence versus conditional convergence versus divergence, there is a special process to go over that, which I will go over pretty soon. However, other than that, there are some things that you want to look out for. So assuming the divergence test does not work, and assuming you don't care what it converges to specifically, and assuming it's not about absolute, conditional versus divergence and all that, then this is how you are going to approach the series. First of all, look for series that have specific forms. These are the geometric series, the alternating series, and the P series. These guys all have special forms associated with them. And so once you can see the special form, or you can algebraically manipulate it to force it into one of these special forms, you can just use the what this table says about those guys to determine that they converge. Another situation is a lot of times you'll see rational functions. This is a ratio of polynomials. Whenever you see a rational function, your best bet is going to be to use some sort of comparison theorem. You are going to use the direct comparison theorem if you can determine which way the inequality is pointing, but use the limit comparison theorem if you can't determine which way the inequality is pointing. This guy is also nice for guys that are almost rational or close to rational. Not a technical term, it's just, that's what I use to describe a situation where when you ignore all the terms that you're allowed to ignore when going off to infinity, if the result looks almost like some sort of rational function, or it looks like some power function 1 over n to some number, then you can apply the comparison theorem with that guy as well. So here, this is definitely not a rational function in this example because of the square root. However, if I ignore all the smaller guys, then it simplifies to this, which simplifies to 1 over n squared, which I can tell converges. So I would actually do a limit comparison with that guy. So whenever you have a rational function or something that's almost rational, if you were to ignore things and consider limit forms, you're going to think comparison theorem. If you see exponentials or a bunch of factorials and you can't really regress into the other situations. Then try the ratio test. It's going to work wonders. Ratio test is a bad idea in this scenario. A ratio test will always be inconclusive for rational functions. The same can be said of the root test. The root test is going to be useful if you see like some mumbo jumbo raised to the nth power or to some constant times n power, because that test allows you to take the nth root and get rid of the power, which is a lot more convenient in general. Then if you realize that you're looking at a series and the function looks like something you could easily integrate, right? So it might look crazy as far as the series is concerned, but if the series symbol was an integral sign instead, you'd realize, oh, that wouldn't be a big deal. So whenever you kind of spot that, like integration would be an easy thing, then all you have to do is check that these three things work out. Make sure that the function is going to be continuous for all real values. Make sure that it's always positive, not negative. Make sure it is decreasing or eventually decreasing. Eventually there comes a point where it just keeps getting smaller and smaller. Then you can use an improper integral to determine what happens to the series via the integral test. That's it. Those are pretty much the standard approaches. Based on what you can see, does it look like a special form? Is it rational or close to rational? Is there a lot of factorials or exponentials? Is there an nth power? Is it an exponential? Or is the thing easy to integrate? These are things you're going to be looking for to actually approach the series. And of course, it all kind of starts out with test for divergence. Always kind of eyeball it to see, does the limit not go to 0? Because if it doesn't, I know it diverges and I don't have to do anything else. One other scenario, was it here? Yes. Is sometimes you're specifically asked to determine whether the convergence is absolute or conditional or diverges. So these are questions that go along the lines of, okay, consider the following series. Does it converge absolutely? Does it converge conditionally? Or does it diverge? When that is the problem type, then what I told you just now earlier, you do that kind of thing, but you do it in this framework. You first apply the test for divergence, as always. If the test for divergence says it diverges, you can just stop the process right there and just say the series diverges and move on with your life. If the test for divergence is inconclusive, then you move down to step 1. Step 1 says check absolute convergence first. You always want to check absolute convergence first. If the series converges with absolute values around the term, then you stop. You say the series converges absolutely. Otherwise, move on to step 2. Step 2 says check conditional convergence, meaning take away the absolute values and check the series as in its original form. Does that guy converge? And if the answer is yes, then you say it converges conditionally. The answer is no, then you say it diverges. Now, of course, when you're checking if the series converges, so here, obviously I asked you to check if things are converging or diverging. That's where you use the strategy that I mentioned earlier. Does it look like a special form? Can I integrate it easily? Things of that sort. One thing that you do want to remember here is the alternating series test cannot check for absolute convergence. It does not. So if you're doing the alternating series test and then you tell me, oh, this thing absolutely converges, I know you don't know what you're talking about, and we'll both move on with our lives. The ratio test and the root test give absolute convergence automatically. So does the geometric series test, gives absolute convergence automatically. If you apply the integral test, you'll also get absolute convergence automatically because the function has to be positive for the integral test to apply, which means when you throw absolute values around it, it's not really going to make any difference whatsoever. So there are a bunch of tests that will automatically give you absolute convergence. These are the geometric series test, the ratio test, the root test, and the integral test. However, the alternating series test can only give you conditional convergence. So that's something that you should be aware of. The signs have to alternate for you to apply the alternating series test. And if you have alternating signs, it means you didn't apply an absolute value. All right. That being said, we left these 4 guys for you to try last time. Now, some of you told me that you guys got stuck. Let's actually go through that now. So we are going to start on that. So let me move some of these guys out the way. Okay, so let's finally get down to the nitty-gritty. Let's get this show on the road. So we started here on 6/23/2020. All right, now this is where you guys can chime in. Did anyone actually get this one? What about the first one? So what is the first thing you do? Test for divergence, right? So step 0, we'll call it, because it's so the first thing you do that you don't even start counting it with a 1. You would try test for divergence. And of course here, that means that you would look at the limit as n approaches infinity of cosine squared n plus 1 over n squared plus 1, and that equals 0. So unfortunately, no conclusion here. The limit equals 0 means nothing. Okay, so what is the next thing we want to do?
Check the absolute convergence.
Right, you're going to check absolute convergence. Which means you are going to consider so you're going to consider this guy with absolute values around this, right? So you put in absolute values, see what happens. Okay, so I have absolute values put in here. What can you tell me about that? What does that give you? Or how did you approach this? So you have this series here. Tell me something that you can know about this series. Any ideas? Was this one? What do you mean still 0? Are you talking about the limit? We already took the limit, so we're not doing that again. Right? Because if something heads to 0, then its absolute value is also going to head to 0, and vice versa. I feel like I mentioned that before. If I haven't, that is actually something you should be aware of. If an approaches 0, then an will approach 0. And it goes the other way around. If an approaches 0, then its absolute value will approach 0. So you wouldn't do a test for divergence again, right? We already did the test for divergence. It's only necessary to do it once. What else can you tell me about that? Any other ideas? Okay, grasshoppers, remember your training. You see a trig function, and especially you see an absolute value. What do you immediately think? No, you would not use the alternating series test. Remember, very important thing.
Is there a
The
ratio?
alternating series test can only show conditional convergence. So that should not come to mind when you want to talk about absolute convergence, right? That's why I put the warning in red and bolded, and I did it several times because it's a very common mistake for someone to try to, oh, let's check alternate. No, we're doing absolute convergence. It cannot be alternating. Direct comparison test, according to Jason. How would you apply the direct comparison test here? So me pointing out the trig function is not for the purpose of pointing out alternating. In fact, this one is not alternating because the cosine is squared. So this is always going to give a number that's non-negative. So even the cosine is not alternating. And cosine n isn't alternating in general. Cosine of n pi is alternating, not cosine of n. Okay, seems the grasshoppers have forgotten their training. You see a trig function in something, you tend to want to get rid of them. You get rid of them by bounding them above by an upper bound. For example, we know that cosine n in absolute values is less than or equal to 1. This is just something that you should automatically think when you see a trig function and absolute values. You see cosine and absolute values, you see sine and absolute values, you're thinking, hey, the cosine is going to be less than 1 in absolute values. So that means this guy is going to be less than or equal to 2 over n squared plus 1. Right? Because the biggest the numerator can be is going to be 2. That occurs when the cosine is the biggest it can be, which is 1. So I see a trig function, I see absolute values. What is the biggest that can be? Well, it's 1, and so the 1 plus 1 will give me 2. On top of that, I can go even further. This is going to be less than or equal to this by making the denominator smaller. Now, of course, because they're absolute values here, that's greater than or equal to 0 automatically, which means we can use the direct comparison theorem. Since the series of 2 over n squared converges, how do we know it converges? Right, it's a p series with p equals 2. Can I scroll back up? So the step 1 is to check absolute convergence, meaning I put absolute values around it. Then I'm like, hey, there's a trig function inside those absolute values. It must have a maximum value that it can be. So I did that. I replaced the cosine with 1 and I get this. Now that is already a lot nicer to look at than the cosine squared plus 1 over n squared plus 1. I can make it even nicer by making the denominator smaller to get the 2 over n squared, the series of that. So now I have this series is less than or equal to that series, and they're both greater than or equal to 0. That is a textbook direct comparison idea. So this means the original series converges. And guess what? I just threw absolute values around it, which means the original series converges absolutely by comparison. Okay. All right, grasshoppers. No, it's late, but get your head in the game. Come on. Bounding a trig function above by a number is textbook. Straight. It's something. It's a knee-jerk reaction that you should have. I'm not saying it's always right, but if you see like a cosine or a sine in absolute values, bounding them above by 1 is pretty much the first thing that you should be thinking about. Right? It's not always going to be it, but it should be like one of the first things to come to mind. That way you can essentially ignore the trig function. Or even if you don't want to ignore the trig function, it allows you to bound things to like apply a squeeze theorem or a direct comparison theorem or something like that. So yeah, that's the first one. Now notice, because absolute convergence works out, I do not move to a step 2. The problem stops here, right? So I stopped at this green line right here. If the series with absolute values converges, stop and conclude the series converges absolutely by this test. And so that's what I did. I stopped and I said the series converges absolutely by this test, right? So there was no need to go to a step 2. Absolute convergence is better than conditional convergence. I don't need to check conditional convergence. I will automatically have it. So yeah, start out checking test for divergence, no conclusion here. Move down to step 1, check absolute convergence. The absolute values around the cosine begs me to replace the cosine with 1. Then an obvious direct comparison becomes evident, and I just apply that. So we're done. All right. So hopefully that's clear. Hopefully we're knocked the rust off our brains just now. All right. We're getting warmed up, getting warmed up. All right, this one. What do we do? What do we do? Test for divergence. Okay, so 0th step, test for divergence. So here, what I would do is I would take the limit as n is approaching infinity. Now the -1 to the n I can essentially ignore. Right? Because I really care about whether or not this hits 0. So if it's going to hit 0, the -1 to the n isn't actually going to matter. So I can ignore the -1 to the n when I'm doing the test for divergence. What do I get for the limit here? 0, how? Right, the limit is 1, right? Which is not 0. So we're done. The series diverges. Nothing else to do, right? See how short it is when the test for divergent works out? Cosine of 0 is 1, and we know that the inside of the cosine here, this is approaching 0. How do I know that's approaching 0? Because I'm a grasshopper and I remember the succession. Log to the base a of n is less than or equal to n to the a, less than or equal to a to the n, less than or equal to n factorial, less than or equal to n to the n. So the n to the n is larger than the n factorial. So on the inside, the denominator is growing a lot faster than the numerator. So the inside of the cosine is going to 0. But cosine of 0 is 1. So the limit goes to 1. Now, once the limit does not go to 0, it diverges. End of story. Right? So that's it. That was the second one. Not so bad. Are we following? Are we good? Okay, all right, good. And remember, don't fall into the mistake of falling into despair and be like, geez, I spent like so many hours on this yesterday. I didn't get that. Just pay attention to what your mistakes were, make note to self, and improve for next time. That's all you can do. I mean, there's no consequence to getting it wrong at this point. I'm not giving you a grade for it. So whatever your mistakes are, just take them as learning experiences and move on. I'll know for the test that I cannot do this. So just learn and move forward. Right, test for divergence, always the same thing. So test for divergence. So I'm going to look at the limit of n over n plus 1 to the n. Okay. And what is that? We're not doing the root test. We're doing the test for divergence. Also, you should be able to see that if we did the root test right here, if you take the nth root of n over n plus 1 raised to the nth power, the root is going to kill the n. Then if you take the limit of that, you will actually get 1. So the root test will actually be inconclusive here, which means the ratio test is also going to be inconclusive. So yeah, not the root test. What is that limit? Just tell me what that limit is. Are we guessing? Like, what are we doing? How about, tell me what type of limit this is, because that might clear some things up with the guesses I'm getting. If you gave this to a Calc 1 student, what would the Calc 1 student notice? Like, what kind of limit is this? It's an indeterminate form, which means you cannot tell what this is just by eyeballing it. Right? This approaches 1 to the infinity, which we know is an indeterminate form. Now, there are a couple of ways that you can figure out what this is. One of them requires that you remember a definition that almost no Calc 2 student remembers. I told my Calc 1 class this, and I told them to memorize it, and they should be able to see it whenever it pops up. But not all of you are from my class, so probably you're not going to see it. So here's a short way to figure this out. And then I'll show you the long way, which is obviously L'Hopital's rule, but this way is going to be quicker. You're going to notice that what we have is this. This is limit. Right, so quick algebraic switcheroo gives us that. Why would I do that? Because there's a formula that I have in mind when I'm making this manipulation. I know what happens to the reciprocal of what I'm seeing there. And so I use that. Now, does anyone know what that approaches? What does this approach when n goes to infinity? No, are you forgetting it's an indeterminate form again? So technically you'd have to do L'Hopital's rule, blah, 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 but this is actually a definition. This is the number E. This is one of the ways E is defined. It's the main definition that you have for E. Oh, I was writing a series. The main definition that you have for E at this point is this. We're actually going to use, we're going to discover another definition pretty soon in terms of series, But in terms of limits, you should know that E is either the limit as n approaches infinity of 1 plus 1 over n to the n, or as n approaches 0 of 1 plus n to the 1 over n. Right, this is a definition of E. So you can notice that, and this will basically give you, well, the limit is 1 over E, which is not 0, which means the series diverges. Let's do the long way, which is probably the way that most people would have seen, but it'll take a while to get through it using l'hôpital. You have to say it with a French accent or it won't work. So I have the limit of n over n plus 1 raised to the n. We would look at this, rewrite it with the exponential, e to the ln of n over n plus 1 raised to the n. This allows me to write this as e to the n ln n over n plus 1, which I would write it as e to the ln of n over n plus 1 divided by 1 over n. At this point, I'd recognize that as n approaches infinity, this is going to approach 0 over 0, because what's inside the logarithm will approach 1, log of 1 approaches 0, and then in the denominator, 1 over n, as n is approaching infinity, that approaches 0 as well. So I have a 0 over 0 indeterminate form, which I need to apply L'Hopital's rule. So now I apply L'Hopital's rule. L'Hopital's rule tells me that I can differentiate the numerator and divide it by the derivative of the denominator. Right? So now differentiating ln of that is going to be annoying. So I would think of this as ln of n minus ln of n plus 1. It's should be an apostrophe s. Its derivative is well, 1 over n minus 1 over n plus 1. So here I would get 1 over n minus 1 over n plus 1 is the derivative of the numerator, divided by minus 1 over n squared is the guy in the derivative of the one in the denominator. Now we would do keep, change, flip to simplify. So this is minus n squared times 1 over n minus 1 over n plus 1. And so this is going to look like combining like terms. This looks like 1 over n times n plus 1. And so this is finally the limit of e to the minus n squared over n squared plus n. That approaches e to the minus 1, which is 1 over e, which is not 0, which implies divergence. So yeah, you'll notice that that limit, if you wanted to do it directly, you have to recognize that it's an indeterminate form. So you have to find a way to get L'Hopital's rule in there. And that is how you would do it.
Jhevon, or professor, one thing to tell you. So for a student who says like it diverges, like but by the root test, like do you think that they would get it correct or
No,
incorrect
it would
if
be
they?
incorrect because it does not diverge by the root test.
But if the student only if they say it's diverges though.
Well, if they show their work, I'll know that they don't know what they're talking about. Like if you apply the root test, what you would look at is the limit of the nth root of an. And this would look like the limit of the nth root of n over n plus 1 to the n. The nth root would cancel the n power. You would end up with the limit of n over n plus 1, and that is 1, which means inconclusive. So the root test is inconclusive here. You can't conclude anything from the root test.
The test for divergence is the correct answer, actually.
Yeah, because the limit does not approach 0. The limit approaches 1 over e.
How would a student get 1 over e like in the first place? Like, can you please scroll up actually?
There are a couple ways. One, if you know what definition of e is as a limit, you can get to it quicker. You can do it here in like 4 lines. Or probably the way that most people go about it is to rewrite it with the exponential and apply L'Hopital's rule. So I realize here it approaches 1 to the n. I need a way to get rid of that power. We learned the basic thing in Calc 1. If you want to get rid of a power, you use a logarithm. So you think, how do I get a logarithm in here? Well, I could log both sides, or I could do this little trick where we rewrite something as an exponential to the logarithm of the thing. Then it allows me to bring the power from the corner down in front. Then it allows me to take that thing from in front and move it to the denominator and write it as a reciprocal. Why did I do that? Because it allows me to get a ratio. And when it comes to indeterminate forms, there are specific ratios that are convenient, namely 0 over 0 or infinity over infinity. So I would rewrite with the exponential, which allows me to rewrite with a logarithm, which allows me to get rid of the power and write it as a ratio. In this case, the ratio is 0 over 0, which is indeterminate, but it's a convenient kind of indeterminate. It's one where L'Hopital's rule is going to work because L'Hopital's rule only works on 2 types of indeterminate. L'Hopital's rule says if you approach 0 over 0 or infinity over infinity, then the limit of the expression, if it exists, is going to be equal to the limit of the derivative of the top divided by the derivative of the bottom, and that gives me this guy. Simplify that, I get this. Simplify some more, I get that. And then ultimately, I end up with this limit. Now, if I take that limit as n approaches infinity, that approaches 1 over e.
Roll up actually 1 second.
And admittedly, this is a difficult problem. So if you're thinking, oh my God, that was difficult. Well, yeah, even the student who sees, who kind of sees what they should do, like a lot of students will actually make a mistake at some point in this calculation. So, I mean, a calculation for a divergence test is not going to be this terrible on a test. However, I kind of like this example. I threw it out there because I do want to hammer home to students that you should remember this definition. So this was just my excuse at some propaganda for that. So yeah, this one is by far the toughest example. So if you got stuck on this one, I wouldn't mind too much. If you got stuck on A or B, then come on, Grasshopper, remember your training. So that was a straightforward calculation, or it should be. It should be one of the first things you think about, which it begs for a comparison. Then for this one, just the test for divergence, you get a non-zero answer very easily. Yeah, this one it's kind of a little mean, but it did give me an excuse to remind people of how L'Hopital's rule works and remind them of a very important definition for the number e. And this also gives you a definition for the function e to the x, which is the most important function in all of mathematics. If I put an x over n, that gives me e to the x.
Good. Professor, may you scroll up a little bit, actually? Go a little up.
Maybe I should do that here. If I do the limit as n approaches infinity of 1 plus x over n to the n, this actually gives me the function e to the x. It's one way to think of the function e to the x. Scroll up where?
Scroll a little up, like, you know,
Here?
a little more up. Okay, a little more. Okay. All right. That's enough. That's enough.
Okay.
Okay, if you take a look at here, like, you know, you have the limit, you know, parentheses n over n plus 1 to the n power, right? And
Yes.
speaking of, like, you know, according to this part, when you go the short way, like, you know, limit 1 over parentheses n plus 1 over n to the n power, what did you have to do, and why did you have to do that?
I do that because I know this definition here. That's why I did it.
And how
Like
are you able to do it?
This here, basically if I combine the inside, I get n plus 1 all over n. If I take that limit, I get the exponential. Now, if I get, not the exponential, I get e. Now, if I look at what I had here, I had the reciprocal of that. Instead of n plus 1 over n, I have n over n plus 1. So because it's non-zero and I know I can just write x as 1 over x, that's what leads me here. I decided to write it as a reciprocal because I know this. So it's a pattern that I'm taking advantage of. A lot of mathematics is taking advantage of patterns. Which is why knowing basic rules and basic definitions are very important, because you see the patterns.
Professor, for a particular problem like this, so if the student says the correct, you know, whether it converges or diverges, if the student says it diverges and that part is correct, but they put the wrong test, will they get partial credit for this type of question?
It depends. I mean, if it's a multiple choice, then yeah. However, if it were a written test and someone used, for example, the root test and told me it diverges, they'd get 0. But for a problem like this, it would be a poorly conceived multiple choice problem. So, because it would be easy for students to get the points without actually knowing what they're doing. But on a written test, then no. Like if you tell me it diverges by the root test, I would have given you 0. Okay, let's look at the last one. Whew. All right. Is there anyone who got this one or thinks they got it? Okay. Now, it's been a while, so let me remind you of what the actual question is. Determine with justification whether the following series converge absolutely, converge conditionally, or diverge. Okay, so when that is the question, what is the first thing you do? Test for divergence. So I'm going to look at the limit of 1 over ln of that, which is 0. So inconclusive. So the next thing, what do we test? Check absolute convergence. So now, what does that mean? You are going to consider the series when you put absolute values around all the terms. So you're going to look at this guy right here. And you're going to turn my pen around. And you're going to, boom, put absolute values around here, boom, put absolute values around here, which brings you into this scenario right here. 1 over ln of the square root of n plus 1. All right. So now tell me about that series. Does it converge? What can you tell me about that guy? I'm not sure what you guys mean by equals 0 or goes to 0. Okay, so I see the first thoughts is that it goes to 0. Why is that the first thought, though? I'm not sure. We already know that it goes to 0 as a limit, but that is inconclusive for the test for divergence. So the goes to 0 thought would have been a thought that already occurred, and you should realize that it didn't take you anywhere. So I'm not sure why you would think that at this point. Yes, this is true. If the an approaches 0, then the absolute value of an approaches 0. But again, that is a limit. That's not a series. We have a series here, not a limit. It is true that as a limit, this approaches 0. But again, that means nothing. If the limit goes to 0, it means nothing. How would you break it up? Comparison test, what would you compare it to? Just use E. There's an ln. There's got to be an E hidden somewhere. Well, technically that's true, but whether or not it's actually useful. Integral test. Do you know how to integrate ln of? Now, here's what I would think. This is actually one of the things where I forgot what number strategy I put it. Strategy 2. But I'll give you guys a hint. This guy is so useful, it's not even funny. It's useful for limits, and it's useful for these guys here. For squeeze theorems, useful for comparison, used for all sorts of things. It's been mentioned several times before. A logarithm is much smaller as n is going off to infinity than a polynomial, which is much smaller than an exponential, which is much smaller than a factorial, which is much smaller than a variable exponential. Does that actually help? It does? I don't know. Are we seeing it? Oh, what are you seeing now? Well, I know you saw it before. I literally told you about it before. I've mentioned this several times. Like, I've seen this before. Yeah, I know for you. I told you. I believe I literally even mentioned it earlier in this lecture. Like, I don't know where it is. Yeah, it's right there. I mentioned it earlier, right there. Yeah. But so how can I use that to my advantage? I think it's one of the easiest ways to see this here. Do we see how to apply this? Ah, Memphis is thinking. I like it. All right. So what if we were to get rid of the logarithm and just look at this as that? Based on what I just told you here, how does this series compare to that series? Bn is greater? Okay, let me ask it this way. The guy on the right, tell me, is it bigger or smaller? Geez, Samia, you think it's smaller? Everyone else is like bigger, 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 bigger. Samia's like smaller. It is smaller, right? It's not exactly like an a to the n. What you can do is you can rewrite the radical as a half power and move the half in front of the logarithm and look at it as log of n plus 1 versus n plus 1. And Samia got it. Once you remove the log, it's actually smaller. Remember, what does a log do? Look at when you have like y equals x, right? It's just going straight up, shooting up. If you put a logarithm in front of that x, what happens? It slows it down. It grows slower, right? When you hit something with a log, it actually grows slower. This guy here is going to be smaller than that guy, which basically means if I take reciprocals, the guy with the log is going to be smaller. So now this is that because this denominator is larger denominator. Right? Because n plus 1 compared to ln of n plus 1, the n plus 1 is larger. How do I know? Because I remember this. So now when I take reciprocals, it flips it because it's 1 over. So the denominator here is larger, which means overall this fraction here is smaller. Now, of course, and yes, I wrote this on the right side specifically because I didn't want you guys to just think knee-jerk reaction. Oh, if you wrote it on the right, it must be bigger. Like, no, tricked you. It's actually smaller. However, now we have that. Now, what can you tell me about this? Tell me about this series right here. The series of 1 over radical n plus 1. Converge or diverge? Diverges. Yes, by p-series test, right? It's like a p-series. Now, the series 1 over radical n plus 1 diverges. It's like a p-series with p equals a half. Right? It's just one step ahead of a p-series, right? You just have a plus 1. So you start one step ahead, but it's going to behave just like a p-series. And so this here was a hint. Logging makes it smaller. So here I have this inequality, and the smaller series diverges, which tells us the larger series diverges. Let's undo. Not the original series. This whole time we've been talking about the guy with absolute values. The series okay, so what can we say now? Right, you have to move on to step 3. So remember the process. Well, step 2, I think we call it because we started at 0. You apply the test for divergence. It was inconclusive in this case. Then we checked absolute convergence, and guess what? It didn't work. We just got divergence. So now we have to move down to step 2. So this last problem, we had to go through all 3 steps. Right? That's why I call it step 3, because there are 3 steps, but it's labeled step 2. So now I'm going to remove the absolute value and see, can I get it to work out now? So I'm looking at this guy again. So 2, check conditional. So now what I'm going to do is I'm going to consider just the original series without the absolute values. Take the absolute values back off. Right? All right, now tell me about this series. What can you tell me about this? Converges and diverges. Converges or diverges, and how would you know? So you see that? What are you thinking? Anyone? Bueller? It's alternating.
Converges conditionally, and as I've said earlier, I even typed in the comments that it is by the alternating series test.
You were typing that when we were doing absolute convergence, which means the alternating series test would not be the answer. You were saying it prematurely, which I expected you to chime in. I've been waiting for you to say alternating series test because you actually typed that a couple times at the wrong point. When we're checking absolute convergence, you should not be thinking alternating series test. At this point is where you should be thinking alternating series test because you have that -1 to the end. So note 1 over ln. If I set an equals this, it is decreasing. It is positive. And an approaches 0. This means the series converges by the alternating series test. And so what can we conclude here? To end the whole problem, what would you say? Right, the series, the original series, converges conditionally. Yeah, so in each situation, when you're checking convergence of the series, you are going to use one of the tests I told you. One thing you have to remember is when you're checking absolute convergence, alternating series test is not an option. You should not be thinking that at all. It's not an option. But yeah, you do divergence tests. Does it work out? If not, if it's inconclusive, move on. Then you check absolute convergence, meaning use any test that's worth using other than the alternating series test. Now, if it works out here and if it converges, then you stop at that point and you say, oh, the series converges absolutely. If it diverges at this point, then what you do is you take off the absolute values and then you do a series test again. And in this case, the alternating series test is the one that I would try because I see that -1 to the n. That reminds me of the strategy that I have here that says, hey, it looks like a special form. It's a -1 to the n. It's right here. So now I see that. Now I'm checking conditional convergence. So the alternating series test is back on the table and I applied it. And I got convergence by the alternating series test, and that gives conditional convergence. So in our first example, so we spent a long time on these, but it's very important because I expect there to be a lot of confusion in applying these, and I think we flushed out a lot of them. Hopefully we'll remember them for the future. In our first example, this actually converged absolutely. We did this by direct comparison. Takeaways here is to remember, you see a trig function with absolute values bounded above by a constant. Get rid of the trig function altogether, and you'll see more clearly what to do. This one converged right away. This one here, the test for divergence gave us divergence right away. This one here, we did the test for divergence, and we got divergence with a little bit of intense computation. But that's just me wanting to remind you what the definition of the exponential is and how L'Hopital's rule could be applied. Then for this one, we actually had conditional convergence, so not absolute convergence. So I gave you like one problem of each type for you to figure out. Test for divergence was inconclusive, so we check absolute convergence. That one diverges. We can get that by comparison. And then when we remove the absolute values, we apply the alternating series test, and then we got conditional convergence. I mean, in hindsight, it wasn't too bad. But the thing is, if you see a brand new series, if I were to just throw a brand new series at you right now, would you be able to take all these things that you learned and put it together, right? So yeah, it's all practice. But hopefully by me going through those, and we went through them very slowly. I mean, in general, a problem like this, I'm thinking 5 to 10 minutes tops per problem. I mean, if it's a problem where the test for divergence is going to show divergence, I expect you to be done in 30 seconds, something like that. So I mean, we did go through these very slowly. In general, you are going to want to be a lot quicker when it comes to a test. So it's going to take a lot of practice, and it's going to take a lot of you looking back at the strategy and really trying to figure out, how can I apply the strategy here? What should I do first? What should I do second? When am I allowed to do this? When am I not allowed to do that? A couple times in this lecture, people are suggesting alternating series tests at points where they should not be suggesting alternating series tests. Another common mistake is people keep looking at the limit. Oh, it's approaching zero. Like, approaching zero means nothing, right? It's in the test for divergence. The only time approaching zero actually means something is when you're applying the alternating series test, and that in and of itself is only applied under the conditional umbrella, which means it's still not something you would look for if you're testing absolute convergence. So all these little things, hopefully, if you made these mistakes, you're writing down in your notebook, note to self, don't make this mistake, I've made it before. And so you should learn from your own mistakes and know what to look out for. So another life tip here is that when you're learning something, and I mentioned this before about how people just think, oh, academics, I never use it in my life. You know, you're thinking too narrow-mindedly. Another thing you should recognize is that this should be at the forefront of your mind. When you're studying, you're not just studying the material. You are also studying yourself. It is very important that you realize this. When you make a mistake, do not just brush it off. Take that as, this is a lesson. This is a part of the lesson. A part of me going through this problem and making a mistake is not just to learn the material, but it is for me to learn about what mistakes am I prone to make. So when you make a mistake, make a note of it and just understand, oh, okay, here's a mistake that I made. Do not make a mistake in the future. Here's why this is a mistake. Make sure I fully understand why I made this mistake so I know how to avoid it in the future. You should be studying yourself, how you learn, how your brain works, what your knee-jerk reactions are, when you have an assumption that's on the money, when you have an assumption that's wrong, and why is it wrong? Why did my brain tell me this was the way to go? What am I thinking about in an incorrect way? These are all things that are very, very important. These are things that you should be paying attention to while you're studying. It's not just about learning the material and learning about series, because yes, in fact, it is quite true that a lot of you will never actually use series in your life. However, the skill of being able to assess yourself, assess your own weaknesses, assess when you can make a mistake in logic, when you don't make a mistake in logic, assess how your brain works and how you can train it to think correctly. That is what is going to help you in life, right? And that is something that studying series, if you approach it correctly, will help you. It will help you in that endeavor, right? This is just a method for you to learn logical thinking and learn about how to correct mistakes, how to think correctly, how to figure out when you yourself are making an error in logic, an error in wisdom, right? When you learn how things are supposed to work and a weird problem shows up in life, and you just know based on general principles of best practices, on general principles of what it means to be a good person or an ethical person, or what it means to be a professional, I can now figure out my way out of this random problem that seems to show up. And the same problem that's going to stumble a lot of people, for you, you're going to know exactly how to navigate it, or you're at least going to know what path you should head down towards, because you are used to being able to study yourself and study how general principles are applied to specific problems, okay? So that is what I want you guys to take away from this. And I want you guys to now really just figure out what is the correct way to think and then drill it in your minds to the point where it becomes second nature, where suddenly you're in a position where thinking in the right way is not work anymore. It's just something you naturally do. And that involves painstakingly going through examples slowly, not only studying the material, but also studying yourself and your own reaction to the material. And by doing these and playing both of these off of each other, you now become a better version of yourself. You become a version of yourself that your knee-jerk reaction is now the correct intuition, right? That's what we're aiming for. Now, when it comes to academics as well as just in general, there is also a third component that you should be studying, and that is me. And by me, I mean your professor, your superiors, the one who are in powers. You should be studying your boss. How does your boss react to things? How does Jhevon react to things? How does my principal react to things? How does my mom and dad react to things? How does
maybe even
anyone
the
in a position of
president.
authority, how does anyone in a position of authority react to certain things? And you need to know how to navigate around that. So for example, if you realize Jhevon put something in bold, in red, he said it several times, you know what? Jhevon is going to react to this particular mistake in probably more of an aggressive way than he would react to some other mistake. So if you're doing a test, what do you think is going to happen if with a certain professor you make a certain kind of mistake? They're going to tend to take off more points. Now your grade goes down. Versus if you're on the job and you know if you make a certain mistake, your boss is really not going to like this one, but he'll let this other one slide. Right? These are the things you should be studying, right? There are three components to studying whatever you're doing. Yes, I know we missed the president. There are three components to what you should be studying at any given time. The actual material, you should be studying yourself, and you should be studying those in a superior position to you, for lack of a better phrase. How do your superiors react to the material, right? You should consider all of these all at the same time. Like I had a friend, and I'm moving on, but just a little bit more. A friend of mine who's also now an instructor. We used to be in classes together, and I used to, you know, there was a point early on in my undergrad career where, man, I was always studying more than I had to study. I was like freaking myself out, just burning myself out to the ground. And I had this friend that I used to study with sometimes, and like I'll be there studying like 50 problems and he'll practice like 5 of them and he'll get a better grade on the test than me. And I'm like, wait, like I'm here doing all this work. You barely read anything. How did you get a higher grade than me? But the thing is, he recognized, you know what? The professor thinks of these problem types as important. So when I'm short on time, I can ignore practicing these types of problems and really practice those types of problems. And he was very good at picking the type of problems that the professor would put on a test. He really understood the professor. And I learned from him that, oh, wow, you know, not only should I be paying attention to the material, but I should be paying attention to the guy at the front of the classroom who's giving me the test. What does he think is important? Because that's what's going to show up on a test, right? And from that point on, I learned, okay, so I should be studying the material and I should be studying myself. That I kind of figured out early. I figured that out when I was a little kid, that both of those are important. When I got to college is when I realized the third component, because that's when work really started getting overwhelming and it was just becoming really difficult to organize everything and manage your time. So you had to become more efficient. And that's when the third component came in. I should also be studying my professor, right? You do that, and then it's like, it's not so bad at the end of the day. All right. And no, you should never be worried. Just learn from what I'm telling you. If you never figured this out yourself, it's not a big deal. Just learn from what I'm telling you, and from now on, go through your life having these 3 things in mind. Whenever I face a problem, there are 3 things that are important for me to figure out. How does the problem itself work? What is my reaction to the problem? And what is the reaction of any superiors in this context to the problem itself? Navigating these 3 components is figuring out a problem. No, it's not, it's not stalking. Because it's thing that happened in public. Like when you see your superior reacting in a certain way, you can say, oh, yeah, I should. Anyway, let's actually move on. Jason, yeah, let's move on. So what I want to talk about now is estimating series. Okay, so we're going to spend some time on estimating series. Basically, I wrote a bunch of things here, but the summary of it is this. The long and short of it is this. The TLDR of it is the following. Figuring out what a series converges to is hard in general. We know how to do this for geometric series, but for us, we don't really know how to do it for anything else. However, we can approximate a series using the partial sums of the series. And things called series estimation theorems help us tell how good an approximation is. So instead of looking at a series and looking at the entire answer, what I do is I look at a partial sum, add up the first so-and-so terms, and use that as an approximation. So when you plug in a series into Wolfram Alpha or your calculator or whatever, and you say, calculate the series, and your computer and Wolfram Alpha tells you, this is the answer, and it gives you 6 decimal places. Wolfram Alpha did not add up an infinite number of things. It is a computer, and that is impossible. What it did was, it added up enough of those things so that you get to within 6 decimal places of the answer. Wolfram Alpha just knows, I just need to add up this many terms to get an answer within a certain degree of accuracy. So Wolfram Alpha knows it wants to return an answer with 6 decimal places. So then what it does is it calculates how many terms of this series do I need to add up to get to the within 6 decimal places of the answer, and I'll do that. So while you give Wolfram Alpha or your calculator an infinite series to calculate, it actually calculates a finite series. It just adds up the first few 100 terms, or the first few 50 terms, or the first few 1,000 terms, and then it gives you an answer. And if you said, I want more accuracy, then it figures out how much it has to add after that, right? So series approximation is a very important thing. And as I mentioned before, approximations are super important because a lot of times in life, approximations are worth more to you than even the correct answer is, right? So approximating is almost as important, and in some contexts, it's more important than finding the actual answer. How can I approximate the answer very efficiently? Right? So this brings us to a situation from where we have to add up an infinite number of terms to where we just have to add up a finite number of terms to approximate what the answer would have been if I could add up an infinite number of terms, right? So that's what this section is about. It's called estimating series, using a finite number of terms to approximate what the infinite number of terms would have converged to. Now, there are 3 scenarios that I normally cover. For us, we're going to cover one because, like I said, it's the summer. The first one is the most important, and it is the one that if you're being tested on a departmental final about this topic, that's the one they're going to test you on. In principle, the other ones work similarly, and I left them here written in the notes, but we're not actually going to do any examples of them. We are going to do 1, the alternating series approximation theorem. Before that, I need to define a new term. We already know what the nth partial sum is. That's just the sum of the first n terms. So if I have a series an where it's a1 plus a2 plus a3 plus da 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 forever, if I add up the first n terms, a1 plus a2 plus a3 all the way up to an, that is called the nth partial sum. And we call that Sn, right? This is the guy that we're going to use to approximate the series. I just want to find the value of n where if I add up the first n terms, it gets me close enough to the answer. Now, obviously, there's going to be a bunch of terms that are left off. In fact, there's going to be an infinite number of terms that are left off. This is called the remainder term, or more specifically, the nth remainder term. So once I find the nth partial sum, whatever is left over at the tail of the series, this is called the remainder term. Now, obviously, the remainder term is going to be the guy that measures the error. How far are you away from the actual answer? So clearly, if you take the magnitude of the remainder term, it is going to be the difference in magnitude between the actual sum S and the nth partial sum, right? If I subtract Sn from both sides, I would get Sn minus S is equal to the remainder term. So the remainder term actually measures the difference between the actual value of my sum and the nth partial sum. So this gives me the error in the approximation. So if I want to add up a finite number of terms to approximate a series, all I need to do is add up enough terms so that my remainder term has an error that is smaller than some tolerance that I would like. It turns out for an alternating series, this is actually surprisingly easy to figure out. And the proof is also surprisingly easy, but I don't want to waste time actually showing you the proof. You don't need to know the proof. So this is called the alternating series approximation theorem. It is a very important theorem for you to know. Right? In fact, I did put in the notes here the integral test approximation theorem. We are going to skip this for the summer, so you can completely ignore this. I won't even ask this on a bonus problem, so completely ignore it. Right? I'm not going to ask you this for sure. Right? So ignore. Right? I mean, you can do it, but don't do it expecting it to show up on a test, because it's not. And there is a theorem that tells you how to approximate a series that you use the comparison theorem with. Skip for summer. So ignore this. There are tests that help you to approximate things with the ratio test and the root test, but those actually get pretty complicated. Even if I had the time, I would not go through that with you, because it's too complicated for Calc 2. It can get really complicated. What we're going to look at is the alternating series approximation theorem, because it's actually surprisingly easy to apply. So suppose you have an alternating series and you know it converges, right? So you have an alternating series, you apply the alternating series test, and you know it converges, right? And it converges to S. Then the following is true. The difference between the actual answer and the nth partial sum is going to be bounded above by the n plus first term. Basically what this means is, for an alternating series, the nth partial sum is within the next term's approximation of the actual answer. So if I add up the first 5 terms, the magnitude of the 6th term tells me how close I am to the actual answer. If I add up the first 9 terms, the magnitude of the 10th term tells me how close I am to the actual answer. If I add up the first 1,000th terms, the magnitude of the 1,001st term tells me how close I am to the actual answer. So for an alternating series, if I add up a nth partial sum, the very next term is going to tell me how close I am to the actual answer. And in fact, the sign of the next term is going to tell me the sign of the remainder, S minus Sn. So that's actually super convenient. Let's actually just jump into an example. So here is an example that we've actually looked at before. This is the alternating harmonic. We saw that this guy converges. Now, we're going to answer some estimations about it. Okay, so here, find Sn. Here it says find S4, right? So we know that this series converges. It's previously shown. We did that in the last lecture. Find S4. This is the 4th partial sum. How do I do that? Well, I just add up the first 4 terms. S4 is going to be equal to, so this guy, notice that this is, if I plug in n equals 1, it's minus 1, plus a half, minus a third, plus a fourth, minus a fifth, plus a sixth, minus dot, dot, dot. That's the series. So what is the 4th partial sum? This part. If I add up the first 4 terms, this is called S4. S4 is just the sum of the first 4 terms. Minus 1, plus a half, minus a third, plus a fourth. I can write all these with 12 as the common denominator. And so this becomes all over 12. And what is that? That's minus 16 plus 6. That's minus 10 plus 3. That's minus 7.
Negative 7 out of 12.
Right. So here, my S4 is minus 7 over 12. Which, by the way, you wouldn't really need to know this, but I calculated this earlier, right? I put this somewhere in my calculator. Just for comparison's sake, this is actually minus 0.5833. Well, it keeps going on through forever. Okay, so that is S4. Minus 7 over 12. So that's, I just computed the fourth partial sum. Now here's the question. How good an approximation is S4 for the entire series? So if I were to, in theory, add up an infinite number of terms, if I were to compute this actual series, how close would this be to the actual answer is the question, right? If I use this as an estimation for the series, how good of an estimation is it? Well, by the alternating series approximation theorem, the difference in the sum and the fourth partial sum, so this is the actual answer here, the difference between that and the fourth partial sum will be less than or equal to A5. And what is A5? This is 1 over 5, right? That is the fifth term. That is the guy right here, 1 over 5. So, in other words, S4 is within 0.2 of the actual sum. Which is crazy that you can actually do that. If you actually add up an infinite number of terms, then you're actually going to get 0.2 away from adding up the first 4 terms. Right? So if your tolerance was 0.2, you know what? Using S4 as an approximation for the series is good enough. So if whatever application you're using, being off by 0.2 is okay, then it's okay. You only need to add up 4 terms. You don't need to add up an infinite number of terms. You only need to add up 4. Right? Now here's another thing. Oh, this is a bonus. Like I don't anticipate being able to ask a question like this. But this question here is relating to the comment that I mentioned here. I put it outside the box because I don't particularly care if you remember this or not. I'm just being honest with you. Remember, study your professor, right? Like I say things like that. Whatever. So S4 is large. Is S4 larger or smaller than the actual sum? Well, the sign of of A5. The sign of A5 is, what was it? Was it positive? It was negative. It was negative. This means that S minus S4 is negative. It will have the same sign. Well, if the sum minus S4 is negative, this would mean that S4 is larger. So to put this into perspective, I have this series, the alternating harmonic. If I add up the first 4 terms, I will be within 0.2 of the actual answer, which means I could be the answer plus 0.2 or the answer minus 0.2. In fact, now with this, I actually know what direction it swings towards. I will be at most 0.2 more, 0.2 greater than the actual sum would actually be. So I know how much I'm off by, and I know what direction I'm off in. So I'm knowing this estimation is actually going to be a little bit larger than the actual value. How much larger? Well, at worst case scenario, it's going to be 0.2 larger. That's the worst case scenario. FYI. The actual sum, minus 1 to the n over n, and goes from 1 to infinity. This is actually minus ln of 2. And I do believe that we are going to get to a point in this class where we're going to be able to prove that. So exciting stuff on the horizon. So it's actually ln 2. This, by the way, is minus I wrote this down earlier as well. 693144718. It's an irrational number. It's a non-repeating decimal, which means the actual difference in S and S4 is roughly 0.1098, which is less than 0.2. So by adding the first 4 terms, I actually got to within 0.2 of the answer. In fact, I'm better than 0.2. I'm actually within 0.10998 of the actual answer. So if your tolerance is, if this tolerance is okay with you, then you don't need to add up an infinite number of terms. That's going to take extra manpower. That's going to take extra computational power. That's going to take extra time. And it might not even be necessary. Why work harder than we have to? Why do an infinite number of things when I can get away with doing 4 things? Right? You should work hard, but not harder than you have to. Because that just means you're being inefficient. Here's another So to answer the question, what is a cutoff for a good approximation? It depends on context. So for us, I will actually tell you what the accuracy is. So for example, in this here, if I want you to be within a certain accuracy, I'm going to specifically mention it, right? However, like in general, especially a lot of your engineers, in general, your tolerances will be known. So when you're like a civil engineer and you're building a building, there are certain percentages that you have to pay attention to, right? So if you're building a building and you want it, you are building an elevator and you know that the capacity, you want it to hold 1,000 pounds, right? Then you're allowed to be off by a certain percentage, believe it or not, give or take. And what engineers usually do is they over-engineer. They over-engineer to the point where if they're off by a certain tolerance in the wrong direction, they're still above what the law requires them to be above. So you would know what the law says. The law says you should be able to have this tolerance. Your elevator should be able to fit 1,200 pounds of people within an error of 5% or whatever. And you just know, okay, when I'm doing my calculations, I have a 5% error. I need to make sure that I'm within 0.05 of what the actual tolerance measurement is, right? So in general, you will know by context what the tolerance is. In a math class, I'm actually going to tell you what the tolerance is. If there's a tolerance that you need to obey, I'm actually going to specifically tell you what it is. So here's a question. How many terms would I need to approximate the series to within 0.01 of the actual answer? So if I use 4 terms, I will be within 0.1 of the answer. But what if I wanted to be within 0.01? I want to be within 1% of the actual answer. How many terms would I need? Well, again, by the alternating series approximation theorem, the error, which is the difference in the sum and the nth partial sum, is going to be less than or equal to the nth plus first term. This means I want the error, which I know is less to be less than we want the error to be less than 0.01. This means we just make sure that the an plus first term is less than 0.01. If I can make sure that my n plus first term is less than that tolerance, we are golden. Let me move these guys. Took off an exclamation. All right, but what does the n plus first term look like? Remember, here our an here, an is just 1 over n, which means that an plus 1 is just 1 over n plus 1. So I just need 1 over n plus 1 to be less than 0.01. This means that I need n plus 1 to be greater than 100. This means I just need my n to be greater than 99. So adding up 100 terms is good enough. S100 is a good enough approximation. So if, for example, Wolfram Alpha wanted to get the answer to a series that you plugged in, it's an alternating series, this alternating series. Wolfram Alpha wants to give you a 2 decimal place answer and be correct to within a rounding error of 2 decimal places. Wolfram Alpha is only going to add up 100 terms of this series, and it will be within 2 decimal places of the actual answer, right? So Wolfram Alpha, when you plug in a series, it doesn't add up an infinite number of things. It actually adds up a few things, a finite number of things, and then it just gives you that answer approximation. Well, yeah, I wouldn't let you add up 100 terms. The question says, how many terms do you need? It didn't ask you what is the approximation. So the idea is we need 100 terms. Right? And that's the answer to the question. This is series estimation. And this is the only estimation that you need to know, the alternating series approximation theorem. There are some others here. I'll leave them up because they were in the notes already, but I will, you can skip them. I was hoping we'd start power series today, but we will move that off to tomorrow, which I'm not too upset at. Power series is kind of a whole new thing, so it might as well have its own day. Power series, again, super important. Such an important application of series. It's not even funny. But we'll do that tomorrow. So that would be 10.7. Estimation, the alternating series approximation theorem, this was covered up in 10.6. So by tomorrow, we should be in 10.7. We might get to 10.8 or 10.9 on Thursday, but remember, whatever I get up to on Thursday, that's what our test is going to be on. So you can essentially ignore everything after that. Well, there's not going to be anything after that. Yeah, power series. It's series on steroids. No, we'll see what power series are. Anyway, that's it for today. So hopefully we learned our lessons by really painstakingly going through these examples. And now you know how to estimate series in one particular scenario when we're estimating alternating series. Tomorrow, we're going to do really exciting stuff. I'm actually excited about it. One of the best applications of series is actually power series. It's so useful. It's not even funny. Series are useful in general, but power series, yeah, they're really useful. And we'll start talking about those tomorrow. Yeah, go struggle with these problems again and struggle with more. Practice from your homework, do more examples from the test, do more examples from the textbook. You can also do a study practice from your online homework. You can ask it to give you some random problems. And yes, Jason is once again pledging his allegiance. We will end right there. And I will, yeah, nothing
Read
else
the
to
rest
say at
of
this
it,
point.
just read the rest of it,
Yes, I'll read it, but I'm just gonna let people go at this point. So you guys can, I pledge allegiance to the flag of the United States of America, to the republic for which it stands, one nation under God, indivisible, liberty and justice for all. More like I pledge obedience to Jhevon Smith and calculus will do. Work hard, through integrity, under expectations, which satisfy Jhevon Smith. Yeah, that's a good thing to go by for this class, but modify that in general. But we'll stop right there. I'll see you guys in the next one, and ciao.